Hi, today we're going to be talking about the organization of matter. It's a very good introduction to chemistry and the nature of matter, what matter is, so forth and so on. And there's going to be a lot of vocabulary terms that we're going to be using throughout most of the year. So it's a good idea to get those done and out of the way now, okay? Now, first of all, we're going to start off with what matter is, okay? Now, matter, as opposed to energy, is anything that has both mass and volume, all right? So any substance has to have both mass and volume. Of course, what's mass and what's volume? Well, mass is the quantity of matter in an object, all right? How much stuff there is inside an object. Now, we often get this confused with weight, but it is technically different. All right. Weight is the force produced by gravity acting on mass. Now, the big difference is mass remains constant no matter where you are in the universe. All right. If something has, I don't know, 60 kilograms here on Earth, it's going to have 60 kilograms of mass in outer space or on the moon or anywhere else. But weight is different. You see, if you have let's say you have an astronaut that on Earth, she weighs 180 pounds, okay? And, fully all geared out and everything like that. On the moon is 1/6 the mass of the Earth. And therefore, it has 1/6 the gravitational pull that the Earth has. So things on the moon weigh approximately 1/6 of what they weigh on Earth. So an astronaut that weighs 180 pounds on Earth would only weigh about 30 pounds on the moon. Okay. Talk about a good weight loss program. But unfortunately, that has nothing to do with the mass. The mass, if they are 60 kilograms on Earth, they're going to be 60 kilograms on the moon. All right. So the weight is dependent upon gravity, whereas mass is independent on gravity. All right. Now, volume is how much three-dimensional space that is occupied by a substance. Okay. And, just how much 3D space does it take up? And matter is composed of tiny little particles called atoms. This is the fundamental building block of all matter. Okay. And the elements, there are a number of elements that are composed of these atoms. And basically, each element is like its own individual type of atom. Now, there are two main types of matter. Okay. It can be kind of subdivided into pure substances and mixtures. And first, we're going to talk about pure substances. Now, a pure substance is a substance with a constant composition and which cannot be broken down by physical means. By constant composition, that just means when you're talking about such a substance, no matter where you go, it's going to be identical. All right. It could be an element or it could be a compound. But if you're talking about table salt, no matter where you go, table salt is always made up of sodium and chlorine, right? It's sodium chloride. That's a pure substance. It's a compound, um, as opposed to mixtures that are not constantly composed. Like you can talk about a mixture like a pizza. Pizza is a mixture, and no two pizzas are exactly identical from each other, okay? But you can still recognize it as pizza, but it doesn't have a constant composition. Now, two main types of pure substances are elements and compounds. An element is a substance that cannot be decomposed or broken down into similar substances by either chemical or physical means. It consists of atoms all having the same atomic number. In other words, the number of protons. We're going to talk more about that in a future lesson, okay? But basically, think of elements being like a whole bunch of different flavors of atoms, all right? Different varieties of atoms. That's what elements are. And all matter in the universe is actually composed of a combination of only 90 of these. All right, the rest are artificially made, but there's only 90 naturally occurring elements. All right, and elements may exist as either, oh, by the way, let's take a step back. This whole concept of matter being only made up of 90 elements, this kind of blows my mind. But if you think about it, think of atoms being kind of like Legos. All right, I don't know about you. I love playing with Legos. Or all right, yeah, when I was a kid, yeah, that's right, still do. And um, if you ever been to Legoland, Legoland's pretty awesome. I used to really enjoy going there with my kids. And they have a place there in Legoland called Miniland. It's in the middle, and they have entire cities all decked out. They got like New York and Las Vegas. They even have Star Wars realms and so forth. And yet, all these different things, whatever your imagination can come up with, are made up of these Legos. But when you look at them, the Legos themselves, there's really not that terribly many different varieties of individual Legos. And yet, with these small number of different shapes of Legos, you can make up whatever your mind comes up with. Think of atoms like that. Individually, there's not that many different individual types of atoms, but you can combine them together in an almost infinite variety and come up with almost an infinite number of different substances based upon how these atoms interact. And that's honestly really what chemistry is all about, is looking at these interactions and what we can make with these different atoms. Real fast, I just wanted to make a correction. Since I recorded the rest of this video, I found out something new. There's always something new in science, but I found out that my information was incorrect. I had before that there was only about 90 or so naturally occurring elements, and the rest were artificially made. I have found that that is not entirely true. There's actually some elements that were originally made artificially, but now that we have made them and know what we're looking for, they've actually found these other elements naturally occurring in small trace amounts in rock, okay, in basically something known as uranium pitchblende. Not to get into too much detail, but I wanted to make sure you guys had the right information. Basically, we used to think that there was nothing heavier than uranium, and everything larger than uranium, like neptunium, plutonium, all of these guys here were all artificially made. They were artificially made originally, but now, as I said, all the way up to 98 California. They have found trace amounts of all of these guys, including technetium down here, which was also thought to be just artificial. But they've now found those existing in nature. Crazy, huh? Who knows? In the future, they may even find larger ones of these. But we'll learn more about these later. All right. Thank you. Now, individual elements can consist of either single atoms, or sometimes you find them as molecules. And a molecule is a neutral group of atoms that are held together by covalent bonds. And we're going to learn more about those in the future unit as well. Now, each element has a specific name and a specific symbol. And we use these names and symbols to differentiate them from each other. Now, a symbol is usually consists of the first one or two letters of the element's name. All right, like oxygen is O, capital O. Krypton is capital K and then a lowercase r. Notice how the first letter is always a capital and the second letter is always a lowercase. Okay, but sometimes the symbols are kind of weird because they are taken from the element's original Latin or Greek name. For example, gold, the symbol is AU. All right, that's from the Latin for gold, which is aurum. And for lead, the symbol is PB from the original Latin word for of plumbum. All right, love that one, plumbum. By the way, that's where since back in ancient Roman days, um, they had very sophisticated plumbing systems, all right, and water aqueducts and so forth. And they made their pipes out of lead. And that's where we get our name for plumbing, is from their word plumbo, all right, because of lead and lead pipes and so forth. Oh, and the gold symbol reminds me of a very bad chemistry jokes. I'm going to be telling you guys lots of very bad chemistry jokes throughout the year. But this one is a gold atom walks into a bar, and the bartender looks at it and says, "Hey, you, get out of here. We don't serve your kind." But get it? Anyway, so as I said, really bad chemistry jokes. Moving right along. So either it's based upon the Latin name or the original name, and so forth. And we use the symbols because it's a lot simpler when we're dealing with writing out equations and so forth, dealing with the symbol instead of writing out the entire name. It's just a simpler way of doing it. It's kind of like in math, we use a single dash, straight vertical line instead of writing out O-N-E for one. All right, it's just an easier way of doing it. And as I said before, the first letter of the symbol is always capitalized, and the second letter, if present, is never capitalized. This is very important in order to not get confused. Because, for example, let's say you have this right here, all right? And capital C, capital O, or capital C, lowercase o. Well, if it is capital C, lowercase o, this is the element cobalt. And it's very different than this. This, because there's two capital letters, this indicates two individual elements, carbon and oxygen. And this is the gas carbon monoxide. And this is very different than CO. So please be very careful when you're writing these out. If it's supposed to be a capital, have it as a capital. If it's supposed to be lowercase, keep it a lowercase. All right? So moving right along. Now, even though there's like 90 or so naturally occurring elements and another almost 30 man-made or human-made elements, believe it or not, only 9 elements make up about 98% of the Earth's crust, the oceans, and the atmosphere. In other words, the part of the world that we can get to. And it's made up of these different 9 elements right here. Oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, and hydrogen. Okay. And when you're looking at these, if you notice, by far the most common element is oxygen. All right. We're going to be dealing with oxygen an awful lot. And oxygen's found in rocks, oxygen's found obviously in the air that we breathe, and oxygen's found in water, H2O. Most of water is made up of oxygen. So it accounts for almost half of all the mass of the Earth that we can get to is oxygen. And then the vast majority of the other elements are extremely rare, and they're hard to come by. All right. Now, a compound is when you take 2 or more different types of atoms and you chemically combine them together. Remember, a molecule is 2 or more atoms, but that are bound together with a covalent bond. But a compound, it has to be, first of all, 2 different types of atoms, and they can be bound together either with a covalent bond or with an ionic bond. But the key thing is that they have to be 2 or more different types of atoms. All right. And compounds can either be covalent or ionic, depending on how the atoms are bonded together. Ionic compounds have ionic bonds where electrons are exchanged. And we're going to learn much more about that. And then covalent compounds have, surprisingly, covalent bonds where electrons are shared. And again, we're going to learn all about this later on. Now, both elements and compounds are types of pure substances. All right, keep that in mind. And again, they're different than mixtures. Mixtures are 2 or more pure substances, either atoms or compounds, that are physically combined together. All right, physically combined. Some examples are like soda, all right, like 7 Up or Coke or whatever. And that's primarily sugar water and some carbon dioxide. And so you have water, you got sugar, and you got carbon dioxide. But because they are combined together physically, we can still sense or taste the individual components of it. Pizza is also a good example. 18 karat gold is one. And some mixtures are homogeneous or homogeneous, and others are heterogeneous. Now, homogeneous ones are mixtures that are exactly the same throughout. They're really blended well together, and you really can't pick out, at least visually, the individual parts of it. Whereas heterogeneous ones, they have different properties in different regions, and usually you can pick out the individual parts. For example, pizza is a good example of a heterogeneous mixture. I mean, you look at a pizza, you can see the different parts. You got crust, you got sauce, you got cheese, you got pepperoni or mushrooms or whatever you put on your pizza, and those are different. So like you can take a bite of one piece of pizza and have more pepperoni in one bite, take another bite, and hey, you don't get any pepperoni at all. So that's why it's heterogeneous. Homogeneous is that they're exactly the same no matter where you go. So they have to be well blended together. A good example of a homogeneous mixture would be a solution like a soda. All right, you take one drink of soda, it's going to taste exactly the same as any other drink of soda. All right, from the same cup. So they're exactly the same. One thing I didn't know about until I started teaching was that you've heard of like 18 karat gold or 14 karat gold or whatever. And that is the differences in the mixtures. Now, pure gold is 24 karat gold. However, pure gold, while that's really cool and has a pretty color and stuff, gold itself is far too soft to make good jewelry. All right. If you're making a necklace, the links would bend or break. And if you have like a ring, then it would get scratches and dings and so forth. So usually it's not a good idea to make jewelry out of 24 karat gold. But you can make jewelry out of like 18 or 14 or even 10 karat gold jewelry because those are what are known as alloys. And alloys mix together different types of metal, specifically at the atomic level. And for example, 18 karat gold is still mostly gold, but you got some silver and some copper mixed in with it as well. And the silver and copper, they make it cheaper, but they also make it harder. And it makes it so that it is more likely to not scratch or be dented or anything like that. The lower the karat the gold, the less actual gold you have. 14 karat gold, believe it or not, is actually mostly copper. Crazy, right? And then 10 karat gold has very little gold in it at all. So you want to be careful. 10 karat gold might actually turn your skin green because that's the copper that is oxidizing. So you want to be careful about getting too cheap of jewelry. All right. So anyways, moving right along. Now, mixtures are often classified by the size of their component particles. All right, there's 3 different types of mixtures based upon the size. Remember, 2 different types based on how they're mixed, homogeneous and heterogeneous. But then you can also break them down by the size of their particles. Solutions, like we were talking about, like sodas, those are homogeneous mixtures with very tiny particles. They're actually broken down at the atomic level. So the molecules or atoms of the mixture can actually come in contact with each other. And the particles are usually too small to see and also too small to settle or be filtered out. Good examples would be soda or salt water. Now, the next size up would be a colloid. Colloids are homogeneous mixtures with a medium-sized particles. And these particles are large enough to see, but not large enough to settle, all right, or be filtered out of the mixture. Good examples are milk or gelatin. I think of like Jello or milk. The particles are so big you can't really see through it very easily. Now, the last one are suspensions. These are heterogeneous mixtures with large particles. These particles are large enough to see and large enough to be filtered out or settled to the bottom. Think of like muddy water or Italian salad dressing, the kind where you have to shake up before you use it. When you first pull it out of the refrigerator, they're often just settled at the bottom, the little, herbs and spices and things like that. So you have to shake it up in order to mix them up. And then after a while, they will settle back down. So if they settle, that's a good clue that it is a suspension. All right. So here's some examples of those. Now, remember, mixtures are different from pure substances. In a mixture, the properties of the mixture reflect the properties of the substances it contains, but the properties of a compound often bear no resemblance whatsoever to the properties of the elements that compose it. For example, there are two elements. One is sodium, and the other one is chlorine. All right. Now, sodium, Na, in its pure form, is a very reactive metal that actually explodes and catches on fire, reacts very violently with water. Okay. And chlorine is a gas, pure chlorine, not the kind that like hypochlorite that you put into your pool, but actual chlorine is a very poisonous gas that if you breathe it in, it actually kills you. It was actually used as a weapon of mass destruction during World War I and unfortunately sometimes afterwards. It was a war gas. And if you breathe it in, it actually will, not to be too graphic, actually to start dissolving dissolving your lungs, and you fill up with blood and you actually drown in your own blood. Really nasty. But those are in their pure form, in their pure substance form. But when you mix them together and react them, they actually make a pure substance that is so safe that we actually eat it. We put it on our French fries and mac down. Yes, I'm talking about sodium chloride, table salt. See, table salt bears no resemblance to either sodium or chlorine. It has totally different chemical and physical properties. That's a compound, okay? But a mixture like pizza, you can still tell what the properties of the individual parts are. If you take a bite of pizza, you can taste the sauce. You can feel, the crust or the cheese and smell the garlic or whatever. Okay, you can still tell the different parts apart, and all those parts of a mixture come together and make up the properties of that mixture, both physical and chemical. All right. We also mentioned this before. Compounds have definite compositions, while mixtures have variable ones. No two pizzas are the same, but no matter where you go, the compound sodium chloride is always made up of sodium and chlorine. Okay? And also, compounds, since they were combined together chemically, they can only be separated using chemical reactions. Whereas physical reactions were what were used to put together a mixture. So you can use physical reactions to separate them apart. You can take a pizza and pick out the pepperoni or the cheese or whatever, and you can separate them physically. All right. Now, this brings up this concept of reactions. Now, elements, compounds, and mixtures can react. In other words, change in three primary ways. The first is a nuclear reaction. Now, this is a change from one type of element to another by the gain or loss of protons. Now, we're going to learn about this later, okay? But nuclear reactions, you actually can start off with like oxygen and end up with something like nitrogen, all right? Different elements are created, all right? For example, carbon-14 undergoes radioactive decay to become nitrogen-14. Now, a chemical reaction, this is one in which It is a formation or decomposition of compounds by the breaking and or forming of chemical bonds. Now, what this does is it basically creates new pure substances, but all the elements remain constant. So the atoms themselves are not destroyed, just the bonds between the atoms are either broken or new bonds are made. All right. So you can react methane gas, like in our lab burners. They burn in oxygen to form carbon dioxide and water vapor. But you still have carbon, hydrogen, and oxygen atoms as both reactants and as products. And then the final one are physical reactions, okay? Now, a physical reaction is a change in the form of a substance that does not affect the composition of a substance. In other words, the pure substances remain unchanged. Now, if I take a piece of paper, for example, all right? So let's say I have this piece of paper right here. Now, this piece of paper has certain physical properties. It has a length, it has a width, it has a color, it has a height, and so forth. These are all physical properties. It's flat, it feels smooth, and so forth. Now, I can change these physical properties. I can crumple it up. Hey, look, I just changed its shape. But is it still a piece of paper? Yes, it still is. I can go and I can change its color. All right. I can go and it starts off yellow, but now, hey, look, it's yellow and black. All right. So, hey, look, the physical properties are changed, but it's still a piece of paper. I haven't really changed what it is. I can change its mass. All right. Now there's less of it, but it's still a piece of paper. These are all physical reactions. All right. But what if I light it on fire? If I light it on fire and burn it, it's no longer a piece of paper. It's gone. And I've combined it with oxygen atoms in the air, and it becomes carbon dioxide and water vapor in the atmosphere. Okay? So that's the difference between physical and chemical reactions. So changing shape, mass, volume, all of these are physical reactions. Also, forming or separating mixtures. And a third example is changing state of matter. Now, we're talking boiling or freezing something. All right? Ice and steam are both made out of water molecules, which is a pure substance. But if I take an ice cube and I melt it and have liquid water, it's still H2O. It's still water. If I boil it and turn it into, steam or water vapor, it's still water. All right. So changing state of matter is an example of a physical reactions. And remember, the different states of matter are differentiated primarily by the arrangement of particles. All right. So solids, the particles are touching each other and they're rigidly held in place. That's why you can't change really the shape of a solid very easily. Liquids, though, they are held into place, but they are physically moving about while touching. Sorry, they're touching, not held in place, but they're physically moving about. All right, so that's like liquid water. Whereas a gas, like steam or technically water vapor, the particles are very far apart and moving around at high speed, sometimes bumping into each other, but still very far apart from each other. That's what makes a gas. All right. And there's actually lots of different states of matter. There's plasma, and depending on who you talk to and what definition you use, it could be as many as like 20 or so different states of matter. We're only going to focus on the three primary ones, maybe plasma, which is the fourth one. Okay. And that's it. Remember, if you have any questions, talk to me, ask for help, come to tutorial, that sort of thing. All right. So good luck, and I'll see you later.